And welcome to this session. Today we will continue our journey into quantum algorithms, and we will actually, after the basics that we have already seen in previous two lectures, look into one of the first provable example of how a quantum speedup can be arranged through an algorithm which is called as Deutsch Jozsa algorithm. Now, it is important to understand that we will split this algorithm into multiple sessions so that we can approach the details in a step-by-step manner. So today's lecture by me is not the ultimate description of this algorithm, but this is just to set the tone so that in the follow-up sessions we will get into more details and actually see how this is happening. To understand the speedup, we first have to look into the basic problem statement which this algorithm is trying to solve. Now, imagine you have a function which is mapping an input to an output, and for the simplicity's sake, let's take the basics example of you have two input, 0 and 1, which gives you two output, again 0 and 1. This function can be now described in two different ways. This function is constant if you have for every input the same output, which means that either you have an input 0 and the output 0, or you have an input 1 but the output is still 0. And the same is applicable in case of 1, input 0 and or 1, and the output is 1 and 1. In such a case, if this happens, what you call is to get a function which is called as constant. Otherwise, the function, if it changes its value from input to output, it's called balanced. Now, the goal is how would you determine whether the function f that has been provided to you is a constant or a balanced function. And for that, you have to logically perform steps which in turns help you get the value of a function. But while performing the steps, you have to see how many steps you are performing to finally get to the conclusion that the function is either constant or balanced. So this is the whole problem statement, and this is what the goal is, to determine the nature of this given function. Now, if you logically think with a piece of pen and paper, classically, if you do this approach for two input to two output, you will end up in performing n number of queries or steps, which is given by 2 to the power n minus 1 plus 1. And if you apply this formula for the two input for n is equal to 2, you have to perform 3 queries. And this is very easy to achieve if you just follow the steps. That first you put 0, then it will either give you 0 and 1, then you have to split it further on both 0 and 1 output and see whether the input of 1 now gives you 1, give you an output of 1 and 0, and then you calculate backwards that, okay, if it is for the different input 0 and 1 the same output 0 0, then it's constant, otherwise it's balanced. Same goes for if for the different input it is the same output 1 1, then it's constant, otherwise it's balanced. And when you logically uh, uh, calculate the number of steps that you have taken, you will see that you have taken 3 queries or 3 steps to arrive at that. Now, quantum, on the other hand, which we will now see in follow-up sessions, will only need 1 query to determine the outcome, whether it's a constant or a balanced function. And this is not a individual case for 2-bit input to 2-bit output. The quantum will work for any number of n, and that is where you will now see that there is an exponential speed up. So for 2 inputs, 3 queries in classical to 1 query needed in quantum, you will see a difference of uh, steps, which leads to exponential speed up. If you expand this input-output scenarios to more than 2 or to hundreds of input parameter, you will see that this number between 3 queries and 1 queries makes a huge lot of difference. And as I said before, this is the first algorithm to demonstrate a provable exponential speed up over classical. So that's why understanding this is very important. So what we're going to do now is, if you have understood the problem statement, and if you have did the calculation by hand to see what's been stated here makes sense, then in the next session, we're gonna look at the actual speed up in quantum and how it is achieved. So I'll stop here today, and thank you for listening, and I hope to see you in the next session. Thank you very much.